gespiegeld.
Nee. Blijf maar elkaar uit.
Dit dingetje.
Ja.
Oké.
Goed. Slide.
Oké,
Maar
dus
ook
als
wel
het niet gaat, dan...
Het zijn ook grote stoelen.
Interessant dat het een spiegelbeeld is.
Ja.
Ja, maar dat gaat wel goed.
Ja, dat gaat wel
Ik
goed.
ben dus ben er wel.
Weet je, mij dat als een
7 uur 's ochtends heeft hij me geësmest van. Maar dit zou ik niet. Dit is
Ja,
Gaat er even facetimen?
Oh ja, we gaan hem natuurlijk ook even...
Of wilde iemand anders?
dat kan sowieso. Maar dan kan ik dit gewoon netjes doen.
Je kan ook even Vince vragen of je wil proberen in te loggen.
Ja. Ja.
een kopie van je verslag.
Ja.
Kan je namelijk je vraag stellen?
Nou, kom maar op.
Toch wel gerepareerd, hè?
Ik weet niet uit de functie verder is dan.
Yes.
Alles. Het is wel heel lastig hoor.
Ja.
Dat moet je toch wel even kunnen vinden. Kom op.
Ik vind het wel een beetje lastig.
Met een andere.
What a pretty pictures. Hij al wist wat dat betekent, dan heeft hij hem niet goed, is hij niet goed bezig geweest voor mij.
Het is de enige die ik hier nu even bij ben.
Ja.
4 eetjes.
Waar staat hij dan?
Ja, als je dat tekeningetje even aanzet, dan is die goed. Ik weet alleen niet hoe het tekeningetje weer weg is.
Nu kan je ook tekenen.
Ja, ik kan hier als hij zo doet, is gewoon een storetje.
Wat was die cijfer? Ik zal vooral veel bewegen. Dat is het gewoon voor.
Ja, dit maar weer even uitdoen.
En geen foto van de Veluca bij Interval dat 5 jaar geleden wind gebruikt werd voor de langste. Nee? Zelf met de biertjes te verleggen.
Zo beetje tijd ik denk van tijd.
Nou, wel met kapitein achterhoeken.
Nou, we zijn hier voor
Inderdaad, iedereen ook bij de borrel ook hier uitgenodigd. En een aantal die komen hier ook en een aantal niet. Dus we moeten maar even zien ook hoe goed het allemaal gaat passen.
Grote zaal met afvuren.
Ja, die waren er niet meer. Alle zalen zitten vol.
Met afsturen.
Ja, alsof iedereen voor september klaar wil zijn.
Ja,
Wie had dat verwacht?
We hadden natuurlijk een uitlaat kunnen nemen, 1500 man.
31 augustus. Hier zit nog een paar dagen voor.
Toys!
wel. Ja, niet gauw voor
Omdat je dan, anders moet je weer college dat voor 2 jaar in.
Dus nog 1 miljard ermee.
Komt per maand.
Ja, we zijn nog eigenlijk niet.
Wow.
Het berichtje is op Harm's telefoon afgeleverd.
Hij reageert nu niet.
Het kan zijn dat hij op zijn nachtkastje ligt.
Ja, hij heeft nog water over zijn gezicht van het gooien.
Icebucket challenge. Een dag geleden op het Schotse eiland. Dus zo enthousiast met het water aan de gang gegaan als het water op was. Ja. Een paar honderd inwoners zo bij één grote watertank.
Meer water maar.
Ja, dat ga ik zo nog.
Niet te veel.
Zeg maar wat.
Een glaspauze in wassen.
Nou, ik heb een paar animaties tussendoor, dus dan zet ik de aandacht. Dan ben ik terug tegen. Nou, zo lang zijn ze ook niet.
Kunnen we repeat?
Heb je nog nooit gehoord? Nee? Ja.
Sorry?
Wij zijn op repeat.
Ja, precies. Laten we nog even de filmpjes die jij hebt gemaakt. Oké. En nu komt je nog met pauze en het
Hij wordt dit trouwens wel 16-9. Ja, maar.
Snap je niks.
En dat is net met QuickTime hebben we hem even getest. En dan is het 4-3. En via YouTube is het 16-9.
QuickTime is altijd alleen.
Ik denk dat het cameraatje 4-3 is. Dat zal dus wel de default zijn.
Hangt van af, hè?
Ja, je kan links en rechts.
Onder en boven,
Ja,
of
of links en rechts.
links.
Ja. Klopt.
Ja, die kijkt live mee via.
En straks ook weer van Martien.
Ja, dus
Komt je het bordeel uit?
Virtueel borrelen. Dus wat het goed is, zijn de goedkoopste gasten.
Nee, maar
Dit
voor
trouwens ook
de
even
verdediging hebben we ook een zaaltje waar ook zo'n scherm op de muur is en een camera die op de zaal is. Dus daar komt hij gewoon via Skype. Ja, is daar een cent tussen?
Zo'n 60 verschil of 70.
Maar hij kan dus gewoon een website liggen.
Ja.
Hij heeft er iets voor aangezet. Ik zal haar een berichtje gaan sturen, komen ze ook op de computer binnen.
Om 3 uur was het zo.
Oh, dat moet jammer zijn.
7
We hebben 1 kijker.
Ik heb maar gezet, hè?
Ja, dat laten we hopen. Iemand is aan het kijken.
We hebben 1 kijker.
Oeh, en iets nog niet.
Oh.
Gok je dat het Harm is? Dat weten we niet.
Zo 10.000 kijkers. Duizenden.
Dit is mijn 15 minutes of fame.
Nice. Hé, die zijn een half uurtje.
Ja, 40 minuten misschien zelfs. Met een beetje pech.
Ik zie nog voor je. Dit is 2 belt. 5, 6 jaar geleden.
Dat hebben we wel eens gedaan.
Op zoek naar een oranje fiets, dat is wel gereageerd.
Oh ja, bij de vierde avond.
Dit is inderdaad zo.
Dat is wat hip.
Ja, ik hoor het.
Dan kunnen wij los dat maken. We gaan het hier.
Dus in de kamer. Van Rotterdam. Oh, ik wil checken de presentatie doen. Check wat je webcam het aan doet. Nou, ik heb er zo'n 6, maar Of er zijn gewoon van.
Hartje taak. De PDA nee.
Nog niet.
Veel succes met deze. Ik had gezien dat ik naar TU Delft ging voor een afstuderen. Zonder hashtag TU Delft. Ja, toen krijg ik even veel plezier op onze campus en wensen hem succes met zijn presentatie. SP.
Oh, dat is het secretariaatsbureau of zo?
Ik weet het niet. Ik zou het niet weten.
Degene die
Ja, het is nog vakantie. In principe zijn nog geen collega's. Ja, het zou van een andere afstudeerwoorden boven. Afstuderen.
But I mean, yes, like the durations. Spinning It's obvious.
Yeah. Nobody cares. Wait.
This is three-dimensional.
Yeah.
And not the fourth thing. Ja, het zit hier in
Waarom is er? Hij heeft beeld en hij heeft geluid.
Dat hoorde die.
Ja.
In de shop?
No, he made it himself. It's
Like
part of the
pottery.
project. It's on page 43
Vortex stretching
of the waterfall.
of the pottery. Are you really good at pottery?
Oh, hè? Hoe kan dat nou?
Nice.
Ah,
Wat is het?
ik stuur hem een sms'je en dan gaat hij antwoorden via Telegram.
Dat is goedkoper, hè?
Dat maakt niks uit. iMessages op het internet.
How many times did you have to print it to get that done? Stapled to one.
Nou, ik heb het getekend daarna op het
Hoe steek?
Ja, dat is stapel.
Gewoon zo'n nieuwe machine. Blijkbaar is dat heel buiten.
Awkward.
Ja, hij hoort dat.
Waar staat het?
Hij hoort ook alles wat we zeggen natuurlijk.
Ja,
Ik weet niet waar dat
Hij
is.
zei van,
Was het niet al over de uitgang?
Nee, dus er stond ook allemaal over
Ja.
uitgang.
ja, we hebben al verbinding met Harm en hij hoort alles wat we zeggen. Het is helemaal goed. Nou ja, alles doet het. Ja. Yes. Oké, tot zo. Hoi.
En als je zo gelachen, dan moet ik wel mee. Ja,
Lachen, niet lachen. Ook leuk. Spontaan.
Ja.
ik zit er zo.
Anders mag je met de kinderen.
die haar lijkt wel heel erg op elkaar tegen.
It does.
That was the look you were going for.
No.
Zet niet
Nee.
op foto.
Maar volgens mij, als je haar recht zou zijn, zou het wel anders zijn.
Nu als ik heb geen idee.
Hoe bedoel je het?
Nou, als ik het ook zou proberen.
Ja, zo dus.
It's weird.
Is it?
It's a bit weird.
Oh. I never see that bit.
Hier, pest nou niet voor de hele dag.
Easy.
Don't look at the bottom.
Maar Harm is dus...
Ja. Als je daar ongeveer staat, zeg maar achter die stoel, dan sta je niet voor het scherm, dan ben je perfect in beeld.
Oké, zo moet ik klik. Zo.
Ja, wat je wil. Ja, je hoeft daar natuurlijk niet constant te blijven staan, maar
Ja,
hij is-
precies. Je moet niet te veel aandacht.
Ik moet niet-
Harm hoort je wel, joh. Dus
Ja,
En hij heeft
precies.
een presentatie ook. Dus.
precies. Dus
Zoals je nou staat, is dat prima.
je moet er niet te zelfbewust mee gaan zijn.
Nee,
dat is
nee.
alleen maar
Dat ik helemaal hier lekker sta.
Ja. Moeten we een kruisje op de grond
Ja,
maken.
expres gewoon hier gaan staan.
Buiten beeld. Oh.
Krijg jij zo weer een vernietigend berichtje over mij? Kan de Jeroen naar buiten, alsjeblieft?
En het geluid van die camera is ook...
Ja, Harm kan het prima verstaan. Hij hoort alles wat we zeggen. En stuurt daar reacties op.
Ik krijg een beetje een Big Brother gevoel hier. Zou die nou ook van dit soort webcams op mijn kantoor hebben hangen normaal? Of,
Ja, je hebt toch dat spuitje wel eens gezien? Een scherm met achter van die scherm monitoren, dat je een beetje heen en weer switcht. Kijk wat jullie allemaal doen.
Bloemetjes erop plakken, dat vind ik.
Not yet? Don't let my family scare. Don't let them scare.
Ga je smartboard gebruiken hier?
Ik was er niet van plan, misschien per ongeluk.
Zo zie je nog het.
Ze zijn best wel handig.
Ja? Ik weet niet of die...
je kan ook gewoon, als het goed is, overal op klikken en dan moet hij naar de volgende gaan. Maar dat doet het niet als je hem, nee.
Werkt alleen als je de standaard PC hebt.
Ja, niet met een laptop.
Ik heb het nog nooit werkend gezien, eerlijk gezegd.
Ik heb het wel eens gebruikt.
Ja?
Het werkt op zich wel.
Nou, dat ga ik niet nu uit.
Maar dat is inderdaad, dat moet je eigenlijk 6 keer geoefend hebben.
Ja.
En dan niet per ongeluk naar iets wijzen en aanraken.
Nee, precies.
Dat je ineens een hele andere desktop ziet of zo. Is dit ook echt een touchscreen dat je ook meteen met je vinger kan tekenen? Dat kan PowerPoint, hè? Als je zo'n scherm hebt.
Zou zo wel kunnen. Ja.
Dat zou op zich dan wel weer handig zijn.
Dus het zijn op zich best wel handige dingen. Maar dan moet je dus wel die computer gebruiken.
Ja.
Dan moet je er ook nog vanuit gaan dat ze die fatsoen is geïnstalleerd.
Als ik zo kijk, zit hij niet eens in beeldscherm. Maar
Ja, die is uitgetrokken. Gewoon hierin.
Oké.
Daar hebben ze ook zo'n switch voor, maar dat gebruikt niemand volgens mij.
Ik heb ook een ethernetkabel losgetrokken waarvan ik echt geen flauw idee heb waar die nou naartoe gaat.
Oh.
Woedend iemand naar binnen komt, dat de computer het niet meer doet.
We zijn de zus kwijt en voldoen.
Maar ik ben er.
En ik heb de telefoon nog met Anne meegegeven. Ik weet niet. Gewoon omdat ik wou Wendy wel dat ik had gevonden.
Of dit is dus 2 niet vinden.
Maar Anne is er een keer geweest.
Zou je denken?
Dat staat op internet.
Ja, ik zou zo wel.
We zijn zo'n technische. Dat is het.
Ik heb er gewoon tekst uit.
Ja, dan wordt het nou check, ja. Dat is
So you can just read it.
Leest het en dan snap je het.
Ja, ik stond netjes met je kop.
Dankjewel.
Oké.
Hoi.
Een beetje uitgeleefd, maar stond met de tocht.
Hoi meid.
Nu maar kijken waar je niet leeft.
Ach, was je. Achterin van de man.
Ja.
Hallo. Nee, het is
Gelukkig wel.
ja, maar dat is niet als er iemand dat is.
Ik heb nog een stukje.
Had jij niet gevraagd? Ja, ben je komen
Fietsen.
Nee, zoals persoon.
Nee,
Oh, sorry.
ja, ik stond voor te wachten. Toen Bauke zei, ze is fietsen en jij mag niet. Dus ik wacht.
Oh,
Ja.
nee.
Gaat wel leven.
Dat ga je achter niet.
Oké. Ja, dat is
Heeft hij eigenlijk een andere sleutel dan? Dat is nog wel interessant. Van de Skype-kamer.
Ja. Ja, die hebben natuurlijk wel 10 minuutjes om daar te komen.
Ja, zou jij hem daarmee? Want wij gaan, hij zal misschien nog wel even omdat hij opruimt.
Ja.
Zou jij dan ook willen helpen bij de Skype alvast?
Ja, dan gaan we met Stefan doen.
Ja,
Ik ga maar.
heb je de sleutel dan van de Skype-kamer ook of niet? Of moet je
Nee, want
straks
die
even
hebben we pas over een uur of zo gelezen.
Ja, nee, maar dat is geen probleem. Wel goed om even te weten.
Ja, dus dat is misschien wel het eerste wat ik moet doen als we klaar zijn. Even.
Ja, geen haast hoor.
Ja.
Dat tijd gaat.
Iemand heeft er niet goed in.
Eerst kijken de euro met sms.
Goed materiaal voor de baby.
Welkom, Stefan Rode.
Ja, is al moeder?
Zo, het wordt zo'n volle bak.
Ja. Misschien moet je die stoel ook alvast even. Ik zal hem wel even.
Het is niet hetzelfde dat
Jij mag toch niet zitten.
Nee, precies. Ik ga gewoon op de grond als ik even nodig. Waar staat Harm? Harm staat die kant zo. Nee, Harm. Ik heb hier nog handjes. Sorry.
Hallo. Waar zijn we dan?
Nou, precies, dat dan via Ernst computer weer.
Ja, via Aaron's computer zit gewoon.
Ja. Nou, daarom uit alles wat we zeggen.
Dat denken we. Of hij is nu gewoon lekker aan het ontbijten.
Toch zijn dit altijd een prettige zaal, maar natuurlijk.
Ik vind dit ook heel gezellig.
Ja, zo collega's. Dat precies het woord inderdaad. Al kale zaal dan natuurlijk.
is niet super.
Wat te drinken mee.
Ja,
Kun je mee eruit.
precies, daar hoop ik het mee te halen. En Mathieu.
Oh, en Mathieu. Ja.
Betrokken bij die big connect.
Wat je bij. Ja? Ja, je was hem zich nu ook voorbereid, ja, dat is nog geen makkelijk.
Vorige week heel vroeg in de ochtend heeft iets verzorgd.
Nou, dit is geen MSP, MSP dan zeggen.
Ik heb een
MSP. Iemand die nog geen staf heeft, die zijn altijd ultra voor.
Ja,
Maar ik vind het alleen maar leuker. Iemand die
Maar je moet zeggen van. Ja, onze is nog op meestal.
We hebben er nou twee.
Twee?
Wat heeft Jessica gedacht zeggen?
Ja, of de zus.
Zij wist het niet tot gisteren.
Ja, is man ook abonnee geworden.
Ja.
Oh, dat is niet het kanaal van mij, hè?
Nee, nee.
Dat zich zo verheugt. Als je die
Ja, dat moet je even vertellen.
voor mij was het allemaal nieuw, dat hele van je eigen broadcasting chat.
Ja.
Dus ik had het, gisteren was ik dat aan tafel. Dus ja, zijn alles zo. Ja, doet er alleen niks mee. Maar goed, hij is nou voor zo'n GoPro gedaan.
Nee, die zijn ook best wel.
Als je die helemaal hebt, dan is het gewoon mee om stunts.
Ja.
Wie is dat?
Mijn zoontje dan. Ja, ja, ja.
Ze zijn hier ook echt. Anders kunnen we het schoenen van de gang liften.
Maar ik denk dat precies past.
Ze moeten eerst vol. Maar zoveel komen er
Maar ik zeg inderdaad.
wel natuurlijk iedereen strikt genomen 5 minuten.
Zal even gaan staan of wat je nu. Ja, dat weet ik wel waar.
Altijd gehad.
Leuk dat je er kon.
Alleen wanneer dat iemand naar in de nieuwe country. Laat we nog
En dan weet ik nog 10 meter. Ik heb wel een zekerheid. Als je 10 of 1 dan
Ja.
Heeft het kamernummer met je weten te bereiken.
Maar vrouwen van vandaag
Ook het kamernummer, of alleen?
Alleen C
Van de hoogste film.
Het begint ergens op de 6, het scant alle gangen af.
Ja.
Ik heb nog handouts.
Succes. Ja, bedankt. Want je kan dan lekker binnenflippen en je niet aankomen. Mensen kunnen lopen en dat ook natuurlijk.
So, welcome everybody, especially family and friends to the Master's Defense of Bauke Rietveld. Welcome also to Harm Jonker, the supervising professor of Bauke, who's currently doing research in America at the National Center for Atmospheric Research, but is following virtually via the internet. So as you know, Bauke did his master's research here in the group Atmospheric Physics here at the TU Delft. As the name implies, we typically consider ourselves, we're trying to understand the physics of the atmosphere, so the flow of air, the formation of clouds and turbulence in the atmosphere. And we typically do that using supercomputers, so really the largest computers of, for example, the Netherlands or even Europe, as Bauke used. And we use that to simulate on a very detailed level the flow of air in the atmosphere. And that's very detailed, of course, as I say that, but I hope also it must be very precise. So recently we were able to do a simulation actually of the weather over a small part of the Netherlands, so around Cabau. And we did that on a much finer scale than typical weather models can do that. So really on a scale that you could simulate individual turbulent eddies, individual clouds, basically. But the fact that you can do that doesn't necessarily mean that you do that better than reality. So this is where we ask Bauke, can you look at how good our prediction is in comparison to, for example, a weather model? And of course, in comparison to the observations, especially wind. So that was what Bauke went doing, and actually when he came back after a while, he came back with some nice results and also with recommendations from, well, you should maybe look at that. So we said, okay, we'll look at that, and meanwhile, maybe you can look at that other very interesting aspect of winds, which is vortices. And vortices can basically be everything between a tornado or a dust devil. So you now gather that Bauke has a lot to talk about today, so I'll say no more, and the floor is yours, Bauke.
Yes. Thank you very much for the introduction. Good afternoon, everyone. Thank you for being here. My name is Bauke Rietveld, and today I will present some of the work that I've carried out here over the past year. My thesis is called Investigation into Wind from Year-Long Simulations and Extreme Weather Using Gales. What this exactly means I will explain shortly. So, wind is the primary focus of my investigation. Luckily, everyone here knows what wind is. Wind is air flowing across the surface of the Earth. This flow of air contains huge amounts of energy. This energy has been used by humans for thousands of years in, for example, milling grain or sailing. More recently, it's been used in wind turbines to generate electricity. However, this energy cannot always be harnessed by humans, as large destructive weather storms can occur, such as tornadoes or hurricanes. So with these wide range of possibilities of what the wind can do, you understand the need to be able to understand and predict these. In order to do that, we need to make observations of wind and study these. Well, this can partially be done using such atmospheric meteorological towers such as this. This is a 200-meter high tower located at Cabau. But you can imagine that it's very hard to obtain complete data for the entire atmosphere using only these few instruments seen here. However, using numerical simulations, this is possible. And often we use a combination of the observations and the results from numerical simulations. So I've now briefly introduced what I've been doing and shown the motivation behind my work. I'll go on to explain some of the theory and basic concepts you need to understand what I've been doing. As stated, I'll use a numerical model. The numerical model I'll be using is Gales, but before we blindly accept the results from Gales, we must test how reliable these are. I will then show how the results from Gales can be applied to, for example, wind turbines in this case. And finally, I will show how Gales can be used to investigate vortices and tornadoes. If you have any questions, please wait until the end, and there'll be more than enough time. So, as mentioned earlier, I will be using Gales extensively throughout this investigation. Gales stands for GPU Resident Atmospheric Large Eddy Simulation, which is a specific type of large eddy simulation, or LES. So the principle behind LES can solve the flow in a given region. It does this by dividing all the space you want to simulate into a grid. Any flow structures which are larger than the grid size, such as large-scale winds or large eddies, can be solved and are called the resolved solution. However, in the atmosphere, there's a turbulent flow, which also has characteristic smaller eddies called turbulent eddies. If these are smaller than the grid size, these cannot be solved, and these are modeled using a so-called subgrid model. The total solution from LES is a combination of the subgrid solution and the resolved solution. Now, in Gales, the subgrid model is a simple eddy diffusivity model, which cannot take into account all phenomena such as counter-gradient flows. Therefore, if results are dominated by the subgrid model, these can be considered less trustworthy. Gales has been used to do year-long simulations around Cabal. This has been called Year of Gales. And this has been done in order to obtain the weather conditions for a wide variety of different conditions. This has been done twice. Once in a domain of 25 cubic meters, and a horizontal resolution of 100 by 100 meters, and a vertical resolution of 30 meters, which exponentially increases to 70 meters at the top of the domain. This has been simply called yoga. And a second run has been done, which has a higher resolution in a smaller domain. This domain is 4.8 by 4.8 by 3.6 kilometers, and has a horizontal resolution of 25 meters and a vertical resolution of 8 meters, which extends to 40 meters at the top of the atmosphere. For both these simulations, they've been have been driven using RACMO, which is a current atmospheric model which is often used. Here we see an example of the results from these simulations. So here on the left we see pictures taken at Cabal for 3 different time steps. In the middle we see the results from Yoga HR, the high resolution run. And on the right we see the results from Yoga. You can clearly see the difference in domain size and resolution as well. You can see that there's certainly a lot of similarities between the 3 different results, but there's also certain differences. Here we also have an animation to show the different conditions that may be obtained. Here we see the weather conditions that are predicted or resulting from yoga for several different days throughout the year. So we can here clearly see that a huge range of different conditions have been simulated, which was the goal of these simulations. So, as stated, I first looked at how reliable are the results from these simulations, and more specifically the wind. To do this, I first looked at the horizontal wind speed profiles obtained from the simulations and the observations. We see the result in this graph where vertically we have the altitude and horizontally we have the horizontal wind speed. In blue we have the result from Yoga, in red that from Yoga HR, and in blue that from Cabal. We see that Yoga HR approaches the result, the observed profile, from an altitude of about 50 meters, and from that point it stays close to it. On the other hand, yoga can seem to have a very different shape, especially close to the surface, and it only seems to slightly start approaching the observed profile from an altitude of 200 meters. Unfortunately, the tower is only 200 meters high, so we cannot make comparisons at higher altitudes. If we consider an altitude of about 80 meters, which is a typical altitude of wind turbines, we can see that the mean annual wind speed at Cabao was slightly larger than that of Yoga HR, which was significantly larger than that resulting from Yoga. So we see these large differences here, but can we understand this and why is this? To do this, we must consider the subgrid contribution to the solutions. In order to look at the subgrid contribution to the solution, we consider the vertical momentum flux profiles, which are shown here. Where again, vertically we have altitude and horizontally we have the vertical momentum flux. The solid lines represent the total momentum flux. The dashed lines represent the resolved momentum flux, and the dot dash lines represent the subgrid contribution to the solution. At the top we see the results from Yoga, and at the bottom for Yoga HR. And here an in-depth study is done for different atmospheric stability cases, but it's easiest to consider unstable cases, so on the left as daytime, and stable cases on the right as nighttime. So, what can we say about the subgrid contribution on this? If we consider that of Yoga HR for unstable conditions, we can see that from an altitude of about 50 meters, the subgrid contribution significantly decreases, and the resolved solution starts to dominate. If we compare this to that of Yoga, we see that this phenomenon occurs at a much higher altitude, from say about 200 meters. If we think back to the previous result, we can see that when the subgrid solution starts to, when the resolved solution starts to dominate, the wind speed profile seems to approach the observed profiles. Finally, if we consider the stable profiles, we see that for both simulations, the solution is not resolved until much higher altitudes. So from this, we can conclude that gales in general simulate daytime conditions better than during the night, and that Yoga HR does a better job at simulating all conditions compared to Yoga, at least for wind close to the surface. If we consider a probability density function of the expected winds we can find at an altitude of 80 meters, we can look at the variation of winds we can expect over the course of the year. Here, again, horizontally we have the horizontal wind speed, and vertically we have the PDF, and the same colors apply as earlier. So in general, we see a fairly good, that all results are fairly similar, and that it's very common to have days with mild winds, and days with above average winds are much less common. If we compare this to the results seen earlier, you again see that Cabao has, the mean value at Cabao is slightly larger than that of Yoga HR, and significantly larger than that of Yoga, which is exactly what we saw earlier. So these results all shown now have been statistical results over the course of the entire year. But with simulations, we can also use these to make predictions. So to do that, we look again at the wind speed at 80 meters, and we look at that resulting from the simulations and compare it to the observed wind speed at that time. So horizontally, in all three graphs, we have the measured wind speed at Cabao. Vertically, we have that from the simulations, where at the top we have Yoga, in the middle we have Yoga HR, and at the bottom we have Drachmo, the driving data. So initially you can already see that Yoga HR does a better job at predicting the results than Yoga. This is as if all the results were to fall exactly on the red line, all predictions would be 100% accurate. So this is clearly not the case, but we can summarize these results in the following table to show it more clearly. In this column, we have the relative root mean square error for the results at this height. And we see that the error at yoga is significantly larger than that of yoga HR and Rakmo, which we saw earlier. And you see that yoga HR has an error of 1.2% less than that of Rakmo. So it improves the predictions made by Rakmo. Additionally, if we consider the error at day and at night, we can see that for all cases, the daytime has a smaller error than during the night. This again coincides with the results we saw earlier. So, what can we say about this? We can see that the difference between yoga and yoga HR is primarily near to the surface is primarily due to the subgrid contribution to the solution, and that yoga HR much better follows any empirical relations, which I haven't shown here, but also better follows the observations at Cabal compared to yoga. And from this we can say that if you're interested in the wind close to the surface, a high resolution simulation in a smaller domain will give more accurate results. And finally, we saw that statistically an unstable atmosphere is modeled much better than a stable atmosphere. Now I will go on to show how the results from yoga HR can be applied to wind turbines. So, one of the most important things for wind turbines is how much power they produce. The theoretical power output from a wind turbine is captured in this following formula, where the A is the rotor swept area, so it's dependent on the rotor size, and U is the horizontal wind speed at hub height. So we can, using the results from yoga HR, we can look at how much power could theoretically be produced for various size wind turbines. And vertically, we vary the rotor size, and horizontally, we vary the hub height. We see in blue, low mean power is represented, and in red, we see a high mean power output. In white, we see how it changes along this white line, so it's seen a bit more clearly. So in general, we can see that for lower wind turbines, with a smaller rotor radius, the power production is much less than that of a high wind turbine with a high rotor radius. We can also see that variations in rotor radius has a much bigger influence than variations in the hub height. So in order to maximize the power production by a wind turbine, the rotor radius should be maximized. So again, this was a statistical comparison. What can we say about the ability to predict the power production? That can be seen here, which is a similar plot to what we saw earlier, but now we have the power production of yoga HR and of Lakmo compared to that which would be obtained using the wind speeds from Cabal. So we immediately see that the spread in the scatter is much larger than what we saw earlier, and from this we can conclude that the power production is much less accurately predicted than the wind speeds. So, can we understand this? This is due to the cubic relation with the wind speed in the formula we saw earlier, and the so-called power calibration curve. This is the power calibration curve, and it shows how the power output of a wind turbine varies with the wind speed. And this captures a couple of phenomena. So for very low wind speeds, wind turbines can't turn yet, so they won't produce any power. Very high wind speeds, wind turbines are generally turned off to avoid damage. There's only a very small area where wind turbines function at most efficiently. If you additionally recall that the most likely wind speeds are all under 15 meters per second, so in this area, we see that if the wind speed is predicted with a certain error, an additional error will be added to the power predictions. If we can again summarize these results in a table, where I've added the table we saw earlier above as a reminder. And here we see the same table for the power production. If we look at the error, we see that this difference between Yoga and Rakma of 1.2% in wind speed leads to a difference of 75% error in the power predictions. This shows that this very small improvement in the wind speed predictions leads to a huge improvement to the power predictions. And this shows why such accurate wind speed predictions are required for wind turbines. So, yoga can not only be applied for the power of wind turbines, but also can say something about the forces acting on them. Here we look at the wind stresses that may act on a wind turbine, where stresses are due to differences in wind speed at different sides of the turbine. Horizontal variations can be called vorticity, and vertical variations can be called shear. And here we look at the mean PDF for various altitudes for vorticity and for shear. If we first consider that of vorticity, we see that it's on average 0, it has a very small variation, and it changes very little with altitude. If we compare this to that of shear, we see that especially in low altitudes, the mean and maximum shear is significantly larger than that of vorticity. This is because at the surface of the wind has a no-slip condition, so there's huge amounts of shear near to this. You can also see that the shear changes greatly with height, and for the highest altitude, so in black, we see that the shape of the PDF approaches that seen for vorticity, which suggests that the turbulence becomes isotropic. Because we see here that the shear is on average much larger than the vorticity, I now can consider this in a bit more detail and how this can vary for different sized wind turbines. So similar to the power power estimations we saw earlier, here we see in red very high amounts of shear and in blue very low amounts of shear. And we see that small wind turbines with small rotors experience much larger shear over the entire, in average over the entire rotor. Whereas very large turbines will, with very large rotors, experience much less shear on average. So in order to decrease the shear acting on the wind turbine, you should aim to, you also see that varying the rotor radius has a much smaller effect than changing the hub height of the wind turbine. So in order to decrease the shear acting on the wind turbine, the hub height should be maximized. Note that this is the mean shear acting over the entire rotor blade, and the maximum shear will always be in the lowest section of the lowest, the maximum local shear will always be in the lowest section of this rotor. So, to conclude this part, we've seen that gales can give valuable information about the wind conditions where measurements or observations are not available or are not accurate enough. And these simulations can not only be used, or can also be used to make predictions, which is very valuable to people working with wind turbines. We saw that Yoga HR can predict the wind speed slightly better than Rakmo, and this leads to a huge improvement in the power predictions. And finally, we saw that the wind speed stresses can be derived from these simulations, where measuring this in reality is very difficult. So, previously I showed that over the course of the year, the shear is typically much larger than the vorticity, especially close to the surface. However, certain extreme weather conditions are characterized by huge amounts of vorticity. These are these vortices. These are dust devils, or in Dutch windhoos, or tornadoes, or as such. So, can we explain this behavior? Can we understand this? Here we have an example of a tornado, and this is such a case of very high vorticity, and this can cause a huge amount of damage due to the huge wind speeds. A tornado is in fact a vortex. A vortex is defined as an area of huge amount of rotation around an axis, which is what we see here. So, how do these occur in nature? Well, in literature, tornado genesis is not. There's no real consensus on how these tornadoes are formed, and but everyone agrees it's a highly complex process with many steps. However, there's one phenomenon which is essential to tornado genesis, and this is vortex stretching. Vortex stretching can be understood if you consider an ice skater turning on the spot. When they pull in their arms, they start to spin quicker. This phenomenon can also occur using wind speeds, which turn slowly and can be stretched to make them turn quicker. And this is a phenomenon required in order to create these huge wind speeds. So to understand tornado-like vortices, we start off by simulating simple vortices in gales. How have I done this? So I started with some preliminary work. And from this, I decided to continue using the so-called Lambda-Scene vortex, which is just a vortex, of which here we see a horizontal cross-section through such a vortex, and we see the flow around the center. And here on the left, we see a radial profile, so how the tangential wind speed varies with the radius from the axis. In my simulations, I defined the radius at which this maximum wind speed occurs. I defined the vortices at the surface, and they are constant in height up to an altitude of h, which I can also define and vary per simulation. And from that point, it decreases to 0, linearly in height. And the area where the vortex is constant is called the bulk of the vortex. All the simulations I've done have been in a neutral profile, which for dry cases in blue we see a neutral profile, and for cases with moisture, the green profile is neutral. The red is a stable profile, which I used in some preliminary work, but haven't used for this. Here we see an inversion height of 15 kilometers. This can be also be varied throughout my simulations. Above this, the air temperature is seen to increase greatly, which suppresses vertical motion. Finally, we need a source of vortex stretching. So we have this Lambda-Scene vortex, which is a large mild vortex, and how will we stretch this? This has been done, I've done this using buoyancy in the form of a hotspot. A hotspot can literally be considered as a spot on the surface which is hot, which heats the air above it, causing it to rise, which causes the mild vortex to become thinner, like stretching an elastic band, which causes this vortex stretching. The radius of, or the hotspot is a Gaussian hotspot with radius equal to that of the vortex. The simulations for this part were done in a domain of 5 by 5 kilometers horizontally, and vertically it rises to 15 kilometers. When using this hotspot, it was allowed to generate an updraft for half an hour, after which the vortex was added to the simulation. So, what does this result in? The resulting setup is very similar to that of a wind hose or a dust devil. And here I have a result of such a simulation, a horizontal cross-section. So, after half an hour, you see the vortex being added. It can be seen to disperse. And then, after a while, you see it reforms. But you can see it's much smaller. And if you look at the wind speeds, they can be seen to be much higher. After a while, you can see that the vortex, the intensity of the vortex seems to decrease, and eventually it's completely dispersed, such as now. Here we see a couple different things happening. We see that the vortex, so it is dispersed, and then it reorganizes itself. This, we believe, is the changing of the laminar vortex, which we add to the simulation, into a turbulent vortex. Further, we saw that the center of the vortex displaces, and it's important that we should be able to find the center of the vortex for every time step, as all analysis is done in a frame around the center of the vortex. Finally, we visually saw vortex stretching, but we need some type of metric to explain this or quantify it. So if we first consider how I found the center of the vortex through this example. In red, we have the initial center where the vortex was initiated, and I make an initial guess as to where the center of the vortex may be, which is here in green. Then in an area around this, represented by the green box, I look for the point with the highest amount of rotation around it. And this is defined as the center of the vortex. Now this is, again, best explained through an animation. And here we see exactly the same horizontal cross-section seen earlier, with in red the initial center and in blue the found center. On the left, we see in red the angular momentum, the mean angular momentum in the entire plane around the midpoint, and in blue the angular momentum around a small area around the blue point. So we see in blue that when the vortex disperses, it decreases, but then when it gets formed again, it increases greatly. And then when it disperses, it decreases again. Whereas if you compare this to the results in red, you can see that the angular momentum in the entire plane is continually decreasing. Further, you can see in this part of the animation that the center of the vortex was not always found very accurately, but for this investigation it was good enough. Here we also see a very nice metric for defining the time of vortex stretching. If we take the time of this second peak, this will give a good metric for how long the vortex is stretched. So, what now affects this vortex stretching, and how can we change it if we want to? Literature teaches us that the swirl ratio characterizes the amount of characterizes vortices. The swirl ratio is defined as the amount of rotation in the vortex divided by the vertical motion. And in our case, the rotation can be defined as the total amount of angular momentum in a horizontal plane in the bulk of the vortex, multiplied by the height of the bulk of the vortex. The vertical motion we can define as the convective velocity scale, W star, which is the characteristic speed generated in this updraft, multiplied by the inversion height, above which no more vertical motion can take place. This RC is the radius of the vortex, and this has been added to keep the definition in line with that we see in literature. This is because in literature, often the vertical motion is not generated from the surface, but is due to a radial inflow of air along the surface, which then gets turned upwards into the updraft. To non-dimensionalize the time of vortex stretching, we use the convective time scale, which is a typical time scale for the updraft time to cycle between the top and the bottom of the atmosphere. So we now have a metric which we believe to affect vortex stretching, the swirl ratio. And we can do many different simulations with different swirl ratios and see if this in fact affects the time of vortex stretching. This result is seen here, where horizontally we have the swirl ratio and vertically we have the time of vortex stretching. The different colors represent what parameter was varied to obtain these results. So here we see that there is a relation between the swirl ratio and the time of vortex stretching. For very low swirl ratios, there's very little angular momentum present in the domain, so there's very little to be stretched. So you can imagine the time of vortex stretching is short. When you increase the swirl ratio, you increase the amount of angular momentum present, leading to there being more angular momentum to be stretched, leading to increased times of vortex stretching. This occurs up to a swirl ratio of about 500, above which it can be seen to decrease again. We believe that from this point, the amount of angular momentum present is so large that the stretch vortex is so intense that it creates a suction at the top. And this suction will pull in air from the top and pull it downwards. This caused downdraft will counteract the driving updraft, which will then suppress vortex stretching. So, as stated earlier, these are vortices which are similar to dust devils. But in order to make them more tornado-like, we need to increase the inversion height increase it to 15 kilometers so that the vortices can be stretched and reach much higher. To do this, we also increase the domain size to about 150 by 150 kilometers, and the altitude reaches 25 kilometers. Further, I've added moisture to the simulations, and this has been done in order to understand phenomena that this, or the effects of this. Here we have a result of such a simulation. In this case, we have a vertical cross-section through a vortex, where the arrows show the flow in this plane, and the colors will represent the flow perpendicular to the screen. So in red, you can imagine wind flowing out of the screen, and in blue, flowing into the screen. So again, after 30 minutes, you see a vortex initiated, and this is stretched, and then it disperses again, which is what we saw earlier. But here, this seems to continually occur. So up to the point of 10 hours, the end of the simulation, this continues to occur. So again, this interaction between the stretching and dispersion is likely due to this suction, this interaction between the suction at the top and the driving updraft. And the reason that it's continually stretched is likely because of this huge domain with a huge amount of angular momentum present. So it's just not all dispersed by the time the first vortex stretching is dispersed, which means it can be just become stretched again and again. Adding moisture means we've added another phenomenon, clouds, which means we can show exactly the same result in another form. Here we see the clouds generated by this result. And again, you see the slightly periodic behavior. And you see the pulsing of the cloud at the top. And this is what we would also see outside if we were to speed up time. So this is what we'd expect. So we see this different behavior, but can we understand this? To do this, we again look at how the angular momentum varies over time for various altitudes for a dry and a wet vortex. And if we compare this to what we saw earlier, you do not see two distinct peaks, what we initially saw, but you see what we saw in the movies, that it's continually stretched and high. If we compare dry and wet vortices, we can see that the vortex is, in the wet case, the vortex is stretched much more intensely. It has much more angular momentum in a small area, and it's stretched to much higher altitude. So you can see that it's stretched up to 10, 15 kilometers high, whereas that wasn't the case in the dry case. So, can we understand this? Well, adding moisture to the simulation can be seen as water evaporating from the hotspot. This moisture in the air can then condensate to form clouds. This releases additional heat, which causes the air parcels to be further accelerated upwards, which can in turn lead to increased vortex stretching, and this increased vertical motion can also lead to this stretching to much higher altitudes. So for these wet, large vortices, we can again consider the swirl ratio phase space, as seen earlier, where again horizontally we have the swirl ratio. Vertically, we no longer have the time of vortex stretching because that's a lot less clear in the cases we see now. Here we have the integrated angular momentum throughout the course of the simulation, which will also give a good indication of how intense and how long vortex stretching took place. Again, we see for low swirl ratios, an increasing the intensity and time of vortex stretching increases up to a point, but then it is, cannot be seen to decrease as significantly as seen earlier. This, again, is likely just due to the huge amounts of angular momentum present, which allows the vortex to continue existing and continue stretching, and not completely disappear as we saw earlier. So, to conclude, this investigation into tornado-like vortices was among the first to simulate turbulent vortices up to an altitude of 25 kilometers. And because this is a new area of research, so many of the results we see here, and we can try to qualitatively understand, but to understand the fundamentals behind it, we're not yet that far. But we can understand what affects these vortices, and we can try to understand what affects these vortices, and this is an important first step. The tornadogenesis, or the vortex generation used here, is very different to that seen in literature, which I explained was very complex. Here, it was seen that these tornado-like vortices can be generated using two simple steps: a large, mild vortex and a single updraft or a hotspot. Well, this can be realized in nature if you have, for example, air flowing over uneven terrain. So let's say water, and you have a forest next to it. The air flowing over the forest will start flowing slower than over the water, causing an initial mild, large-scale rotation. Well, then the only thing you need is a simple updraft to generate this tornado-like vortex. If this occurs in nature remains unknown, but it is a very easy method to generate these vortices, which can easily lend itself to future research. Further, I showed that there's a seemingly fundamental difference between these large and these small vortices. And this leads to the idea that the use-swirl ratio in this investigation may not be 100% correct, because for dimensionless numbers you do not expect this. However, these are all very interesting avenues of research which may be possible in the future. That was it for my presentation. I have one final animation for you. This is, again, this large wet vortex at a higher resolution, where we release all these particles, these balls you see, into the flow. And you can consider these balls as cows being released into a tornado, and how they move, if it will work. Try again. So we see how particles in this flow would move. So you see it's slower flowing on the outside, and the inside is really turning a lot quicker. So that was it for me today. Thank you for your attention. Are there any questions? Yes.
Yeah, really cool tornado stuff. But I actually want to go back to the, well, slightly less awesome part of the yoga high-res part.
Yes.
You said that if you go to a higher resolution, you can improve wind speed predictions.
Yes.
But I can also imagine that if you make the resolution smaller and smaller, at some point you have to take into account forests, houses, and all other ground stuff.
Yes. That's one thing I also wrote in my report, that comparing these two, you could see that a decreased domain size has a good effect on the wind speed near to the surface. But there's definitely a limit. If you start having a domain of 100 meters, you cannot in no way capture all the large-scale effects. So there will be some optimum in there, but it could possibly be, yeah. So it's somewhere in between the range of what we've seen here, and possibly smaller. And where this is also a possible avenue for future research if you would really want to apply gales to wind turbines or such effect.
So your first part of your research, you compared the LES results with results from a weather forecast model.
Yes.
And then in the second step, you're going to simulate the tornadoes, and you're able to show that the LES model we are using is capable of reproducing those tornadoes. Now the other way around, do you think that the weather forecast model is capable of reproducing tornadoes?
I'm not an expert on weather forecast models, but I believe these are generally much coarser resolution and much larger grid boxes, if I'm correct. So you do need a very high resolution in order to simulate these tornadoes, because you have these huge amounts of vorticity, so these huge variations seen in only a couple of grid boxes, even if you use a very fine resolution. So that is really essential to capturing such phenomena, because if you do not have these very small grid boxes, there's no way you can capture these huge variations.
A question regarding the wind speed forecasts. So if you go to slide 13, I think it is. Yeah, or that one. So, yes. So you state that Yoga HR, so the middle plot, so it's more accurate than RUCMO, at least at this height.
Yes.
Can you give an indication? Because if it goes lower, you said, for instance, it was worse, but is it also worse than RUCMO? Have you looked at that?
I haven't really considered how this changes with altitude, and I'm not quite sure what would happen with RUCMO. But if you consider the wind speed profiles, so this one,
yeah,
you see that 80 meters, so the altitude of wind turbines, very nicely coincides with the point where Yoga HR starts to approach the observations. So this is, in that sense, this is very luckily chosen height of these wind turbines to use the Yoga HR. And yeah, you can. So for this, you can already see that for lower altitudes, there'll be larger variances and larger errors. I'm not sure what would happen in RUCMO in that case.
Right.
Yeah, I also have a question. I'm actually a bit stunned by the 75% increase in power forecast skills.
Yes.
And I was wondering, does that assume the cubic law all the way, or did you use that?
This was including the power calibration.
Okay. Even then.
Because in this area, say you saw that the mean wind speed error is 1 or 2 meters per second. So if by 1 meter per second you have this additional error in absolute power production, which you add on top of the error due to the cubic relation.
Wait, sorry, I don't get it.
So the error in wind speed is cubed, or how the error. So that increases the error, and then say this is what you measure and this is what you actually have.
Yeah.
You have this 20 or 30% difference, which you add on top of that.
But that is the cubic
No,
regime, right?
here is the cubic.
No. Isn't
this is the absolute power divided by the theoretical power.
Oh, okay. Oh, I'm sorry. I thought it was what they call the turbine power curve.
Yeah, this is I think generally called the power calibration curve.
Yes.
It may or may not be the same.
Okay, I see. Interesting.
Yes.
So that's an interesting perspective.
Yeah, it was also an unexpected result for this.
I have a question. As far as I understand, in the model that you use a homogeneous grid. So basically, the size of the cells everywhere in the model is the same, apart from when you go to sort of the subscale where you have things that you add to it. I think from the curves that you showed, the least accurate your model is actually when you are close to the Earth.
Yes.
That's where those small sort of influences actually have a large contribution. You showed then that the HR solution, because it has a smaller scale, basically gives you better results.
Yes.
Is anybody looking at using variable grids where closer to the Earth you actually have sort of the HR scale size, and as you move further up you go to larger scale? So it would be a different formulation in terms of the model that you use.
We already slightly have that because vertically the altitude or the grid size changes. It's smaller close to the surface than at the top. And there are, I believe, Richard, the other master student, is currently working on how to improve this. And I'm not 100% sure on how this is being done. But there are people working on this. Yes. One final question.
Yeah, the difference between RUCMO and Yoga HR. What would be another advantage of having a high-resolution model like the Yoga HR results? Regarding, I'm thinking of gusts and that kind of variability that you cannot model in a weather prediction model.
Yes.
Can you comment on that?
Yeah, so as you say, gusts, or what Stefan asked earlier, these vortices, or things that require changes on very small scales, these cannot be captured in these larger scale models. And those are the advantages of these higher resolution cases. But of course, these higher resolution cases require much more computational power. So you have to find a compromise somewhere. What you want to capture and how much money you have.
Would that also influence the power forecast and the accuracy of it, or something that could be used for the wind energy production?
I'm not too sure. I can imagine that. What we said earlier, that this increase in resolution already leads to better predictions, and there's somewhere an optimum in there which will probably lead to the best possible predictions using such a model. So and the best possible predictions will take into account gusts and if a tornado were to come by, of course, if possible. But the question remains, what this would be, where this would go.
Okay, if there are no more questions, then I think that this ends the public part of the defense of Bauke. Bauke himself is not finished. We will now have a closed private defense with myself, with Stefan de Rode, with Mathieu, and also with Harm, but via Skype connection. So I would like to ask the family to retreat and maybe have a drink or something for a while, and then we'll have to take Bauke apart for a moment.
Literally.
Oké, snel mijn computer. Pak even mijn computer. Doe het hier, hè?
Nee,
Skype-ruimte. Ja. Nou, ik voel het test. Gaat iemand die als het misgaat, gaat iemand heel goed snappen?
Maar ik heb gezorgd dat we geen angst van steeds zijn.
Dat is best groot. Ja.
Het eerste wat ik wilde hebben was een stift in de appeltjes zwart.
Zo. Jij gaat de kamer ja?
Even weg. Je ziet niet de rest van de wereld.
Nee, dat is het niet. Niet.